back pocket.
When you're not looking, I'm gonna be like.
All right, so we're going to do chapter or section 3.3 today, which is some stuff that you've probably already done the procedure. Yeah, you've done the algorithm called division algorithm. You've done it before. I don't know though if you've ever taken the results and seen what the results meant to you, okay? And developed kind of a meaningful understanding of what we're doing, okay, and why we do it. But if you remember from last year, you've probably heard the words long division for polynomials. You've probably heard the phrase synthetic division, right?
Nope.
Okay, yes you have. But we're going to take those two things today and revisit them, but then talk about how they introduce to us what we call the remainder theorem and factor theorem. It becomes very important for us to be able to take any polynomial of any degree and break it down to its factors. Okay, so we know how to take like x squared, I don't know, plus 5x plus 6, and break that down to x plus 2 times x plus 3, right? Okay. We're now going to say, okay, what if I start with like x to the 6 plus 5x squared plus 15? How can I break that down to essentially it's 6 different factors, okay? And it all starts with long division and synthetic division, okay? Now, the long division stuff, we're going to visit, we'll talk about a couple times, but ultimately, we're going to be focusing on synthetic division because it's one, it's simpler, two, it provides us some unique information when we get a result, and it's easier to kind of write out. All right, so long division, just some stuff that you know from maybe like the 4th grade, 3rd grade. I don't know when you start dividing, but the terminology that we're going to use is going to be consistent. So I want to make sure that we understand this. You know, a lot of times, so we see division this way. Maybe we'll see it this way as well. 38 divided by 7, like that, right? Okay. And as you get answers, so the 38, we call that the what? Dividend. Okay. Dividend. The thing that is doing the division, the thing that we're seeing, how many times does it go into the dividend? That's called the divisor, right? Okay. The amount of times that it goes in is referred to as the quotient. Okay, so the 5 there's the quotient. And whatever's left over, you guys know as the remainder, right? So those are terms that we're going to use. Understand that we should be able to get the same thing kind of over here, okay? And when you guys we're in like 2nd grade, 3rd grade, 4th grade, we start introducing multiplication and division. A lot of times you ask yourself, how many times does 7 go into 38? I don't want to think about it that way. I want to think about what number can I multiply 7 by to get something either exactly to be 38 or very close to 38. Okay? And really I want it to be less than 38. That means I don't want it to be bigger. Okay? So what number would that be? 5. So 5 times 7 gives me that 35, right? Get my 3, and then you guys in like 3rd grade put R3, right? Remainder 3, okay? But we know that that means the same thing as if I had 5 total things, okay? And then I have left over 3 out of a total of 7, right? So 3 sevens. And if I multiply that back out, so we either put a plus sign here or just made it as a mixed number of 5 and 3 sevens. 5 times 7 would be 35, plus 3 gives me 38, so I get 38 over 7 here, right? 38 divided by 7. So that procedure, that process is going to be the same for what we do today. It's just with polynomials, okay? So it's not going to be that easy, but the logic is the same. You have a question? Benson, do you have a question?
No, I was just saying arduous.
Okay. So this is what we come up with what we call the division algorithm. Okay, and this is how we divide polynomials throughout long divisions. It says if p of x and d of x are polynomials, okay, where d of x cannot be 0. If d of x was 0, you'd have division by 0 right here, correct? Okay. It says then there exist unique polynomials q of x and r of x. Q of x being your quotient polynomial, r of x being your remainder polynomial, okay? Where r of x is either of 0 degree, so that means that it's a constant, it's just a number, okay? It's probably an integer. Or of a degree less than the degree of d of x, okay? So if d of x is like x to the third, r of x would be x squared. Does that make sense? Okay. Such that we get these two statements. And these two statements are really the same thing. Okay, it says the polynomial p of x divided by d of x, p of x divided by d of x is equal to q of x plus the remainder of x divided by the divisor of x. Okay, so going back to the last thing we did, the 38 divided by 7, this would be the 5, this would be the 3, and that would be the 7. Does that make sense? Okay, but now we'll have some, maybe a quadratic here, okay, and then a constant term over maybe a linear term, okay. But if we think about this, just this generic phrasing, if I go ahead and multiply this entire equation by d of x, okay, what's p of x over d of x times d of x?
P of x.
P of x, right? It gives me that right there. So that cancels out with that. Okay. Now it's q of x times d of x.
Q d of x.
Yeah. Qx dx, right? Or dx times qx. However you want, that's multiplication is commutative, right? We can flip flop that. Okay. And if I multiply rx over dx times dx, does just give me rx or r of x. So these two things are analogous. They're the same. Okay. And they're going to ask us to be able to flip flop between the two of them. All right, we'll do a couple examples of that today. But if you understand what we just did there, you'll be fine. There's also some stuff where we think about common denominators that makes it easy to kind of convert back and forth between the two formats. So the polynomial p of x and d of x are called the dividend and the divisor. P of x being the dividend, the thing that you're dividing, and d of x is your divisor, the thing that's doing the division. And q of x is the quotient, r of x is the remainder. Okay, so those are, again, similar to the statements that we made earlier in 4th grade. Alright, so doing examples, okay? They're going to ask you, can you take, and they'll write it out a lot of times, kind of like in that first sentence. They won't structure the problem for you. They'll just say divide this polynomial by this polynomial, and then you have to set it up and all that kind of stuff. Okay. So when we ask to divide something, okay, they're saying that is your p of x, that is your dividend. Okay. By x minus 4, that means x minus 4 is the thing doing the division, so that's your divisor. Okay. So we set something up that looks like this. Okay? That's the division initially that we're going to do. This is long division. And we're going to talk about how we do this long division and how we can simplify things using our synthetic division process. But when we do this, the x minus 4 of 6x squared minus 26x plus 12, kind of going back to what I tried to get you to think about when we did this. Okay? Don't think how many times does 7 go into 38. Because it's going to be really hard to figure out how many times x minus 4 goes in to 6x squared minus 26x plus 12, right? The alternative approach is to think about how many times can I, or what can I multiply 7 by to get that 38, right? Okay, or something less than that 38. So that's kind of the same idea here. What can I multiply this here by to get 6x squared? Okay, that's what we're going to think about. Now, if we understand what we're doing here, if I multiply, I'm thinking about a monomial that's going to go right here. Okay? So I'm going to have a monomial times a binomial, and I have to distribute that, right? So I'm really only interested initially and multiplying that x by something. Okay, don't even worry about the negative 4 right off the bat. So you're thinking, what can I put right here so that I multiply it by x? It gives me this 6x squared. And what number would that be? Or what term? 6x. Okay, so I'm going to put 6x there. And now we're going to go through and say, okay, just like we did up here, we put 5 up there, right? And we went 5 times 7. You got 35. Well, now we go 6x times my divisor. And my divisor is a binomial. So you have to distribute that. So I'm going to 6x times x gives me 6x squared. And then 6x times negative 4 gives me negative 24x. Okay? And just like here, you know, we put 35, we put a little line there, and then you do subtraction, right? Okay? Now, what's another phrase for subtraction? Okay. But what do you learn as its definition in the 9th grade, 8th grade? It's different, but it's adding what? Adding the opposite, right? Okay, so I want to, because we're going to subtract these, but I think that's problematic for people because, you know, 6x squared minus 6x squared, that's easy, right? But think about how you get to this one here. You go negative 26x minus negative 24x. People struggle with that, right? Okay, subtraction is more difficult than addition, right? Okay, so let's go ahead and apply the definition of subtraction. Say it's adding the opposite. So let's just go ahead and multiply this entire row by a negative 1. So it changes every sign through there. And now it just makes it a little bit easier. Now you can just add straight down. Okay, so adding straight down, those go away, right? And you're left with, what, negative 2x. Okay. Now, think about what you would have done up here. Instead of being this maybe being 38 divided by 7, maybe it was 380 divided by 7. When you think about how many times, or what we need to multiply 7 by to get something close to 38, we chose 5, and then we brought the, we did that subtraction, got our 3. And then what do we do with that 0? Bring that 0 down, right? Okay. So what do you think we're going to do with this 12? Bring it down. Okay. And it's really no matter how many terms are there. If there's 3, 4, 5 other terms that we haven't talked about, we bring them all down. Okay? You bring every single part down. And now, the reason we call this an algorithm is it's kind of a process that you go over. You do the same thing and repeat until you have something that signifies that you have completed the process. So we're going to do the same exact steps. But now, instead of trying to think about what multiplies together to give me 6x squared with x minus 4, we're thinking about what can I multiply by x minus 4, or just really the x, to get negative 2x. Okay? So now we're looking at that line right there. So what do I need to multiply x by to get negative 2x? Negative 2. So I'm putting negative 2 up here. And now I go through the next step of the algorithm, which says multiply that negative 2 by your divisor. So what's negative 2 times x? Negative 2x. And then negative 2 times negative 4 gives me positive 8. Okay. Now, I like to add the opposite, so I'm going to go through and I'm going to change all the signs. If you don't want to do that, if you don't like changing all the signs, or that you know that creates a problem and you're fine subtracting, say negative 2 minus negative 2, and that gives you 0, or 12 minus 8 is going to give you 4. That's fine, you can do it that way. I'm always going to change that row, multiply by negative, and add straight down. So that's going to give me 0, right? 0x, and then 4. Okay? Now, the algorithm tells us we're done. Okay? And how do we know we're done? If we go back to the PowerPoint said right here, says where r of x is 0 or degree less than the degree of d of x. Okay? So the degree here, let's think about this. The degree here of d of x, it's like a p, d of x, that degree is 1, right? This degree, we knew we were not done at this stage here because that degree is 1 and that's not less than d of x's degree, right? So that's kind of the identifier to keep going. But now I get down here, okay, and the degree here is actually x to the 0, right? Is that degree of 0 less than the degree of d of x? So that tells us we stop at 4. Okay? And that becomes our remainder. So this was d of x. Okay, this inside here was your dividend p of x. 6x minus 2 becomes your quotient, and 4 was your remainder. So I like to identify those parts, because now the next part is not to stop there, but to actually write down what all this means to us. Okay? If I were to write this down, you want to use both formats that they provided. One of them was that p of x divided by d of x was equal to, okay, your quotient plus your remainder over your divisor. Okay? So I'm going to take all those parts and form fit them to this. Okay? So that tells us that 6x squared. Now you usually wouldn't write this part here the way I'm going to, but I want to show you kind of a connection with what's going on here. So we go 6x squared minus 26x plus 12. That thing divided by x minus 4 is equivalent to, now your quotient, so your quotient was 6x minus 2, okay, plus then your remainder of 4 over your divisor of x minus 4. Okay? So those two statements, that one there and that one there, are equivalent. Okay? And what we're going to find out is that one on the right is a lot better format than the one on the left. And it's a lot more informative to us of what our function is doing, what our graph looks like, than what this one on the left is. Okay? Furthermore, think about this. If I were to look at this thing over here, okay, you've got essentially two fractions there, right? Okay? Two fractions there, which I'm adding together. Right? 6x minus 2 over 1 plus 4 over x minus 4, right? If I wanted to add those together, what do I need to add those together? Common denominator, right? Okay? So let's do that. What's the common denominator going to be? X minus 4, right? So I'm going to multiply this by x minus 4. Okay? And, you know, how we deal with this process, and, you know, multiply that by x minus 4. Okay? So if I do that, I get, you know, 6x minus 2 times x minus 4. Okay? And that's going to be all over x minus 4. Right? We maybe go the long way here. That's going to be over x minus 4. And then this thing over here is going to be 4 over x minus 4. Okay, really, like I said, I need to multiply that by x minus 4. But if I've got the denominators the same, what's that tell you about your numerators? Come over here. I had 6x squared minus 26x plus 12. And this was x minus 4, right? If this is an equation, these denominators are all the same, what's that tell you about your numerators? They're the same. So, this tells us that 6x squared minus 26x plus 12. The dividend that you started with, right? The p of x that you started with is equal to, okay, 6x minus 2. Well, that ended up being your quotient, right? Okay. Times x minus 4. Well, x minus 4 was your divisor, right? And now plus my 4, which wasn't that your remainder? Does that kind of make sense to everybody? So you're seeing there that p of x is equal to the quotient times the divisor plus the remainder. Okay? If you were to take this thing here, FOIL that out, 6x times x gives you 6x squared. 6x times negative 4 gives you negative 24x, right? Negative 2 times x gives you another negative 2x, so that's negative 26x. And then negative 2 times negative 4 gives you 8, right? So far, just FOILing that out, you get 6x squared minus 26x plus 8. Well, add 4 to that 8, and you get plus 12, right? Okay? So what that allows us to do is take our polynomial p of x and basically break it down a little bit, make it look a little bit nicer than what we started with. Okay. Now, what would be really nice is if that remainder goes to 0. Because if I have a polynomial that I've divided and I get a remainder of 0, think about what this would have been. Let's just say this would have been like a plus 8 here instead of a plus 12. Then this would have been a 0. I have no remainder. And now this went from, like this would have been an 8 there. This thing would have gone from 6x squared minus 26x plus 8 down to this thing. And does that tell you where your graph crosses the x-axis? Those are not linear factors, right? Those are zeros. So that's kind of the purpose and the necessity of being able to do this long division. All right. But that practice there was just trying to show you that p of x over d of x, when they ask you to write it this way, quotient of x plus the remainder over the divisor, okay, that is saying the same thing as p of x is equal to d of x times q of x plus your remainder of x. Okay. Those two things, we want to be able to flip-flop back and forth between those two. Just depending on how they ask you in WebDesign, how they ask you on the test, be able to flip back and forth between those two and understand what each one is telling us. Now, that's kind of a pain in the butt to do. That long division was a pain, right? Okay. So let's change things a little bit. Let's make it a little bit easier. Okay. We started with 6x, and let me just go ahead and go back up to the beginning and we'll delete everything and start over from scratch. So that thing is ugly because it brought in, it was a lot of writing, a lot of kind of notation stuff. Let's simplify things and let's just write down our coefficients. Okay? So come down here and write 6, I'll write negative 26, and I'll write 12. Okay? When I write down my code, I'm taking my dividend and I'm writing down just the coefficients of every single term. Okay? And we'll talk about some unique situations here in a moment that we got to pay attention to. But one of the biggest things I see when people make mistakes with this is that they forget to take the negative signs with them. Okay? So it is negative 26. That has to, that negative is part of that term. Then the next thing you do, if you remember this from last year, you put a little box there, and you're going to put some value in that box. Okay? And the way we do this is if this here is x minus some c, right? Or let's actually write it as x plus some c. Okay? We are going to take that little thing, set it equal to 0, and solve for x. So if I solve for x, it'd be x equals the opposite of c, right? So what that tells me then, if my c was negative 4, then what's going in this box is the opposite of negative 4. You always put the opposite of what that term right there that you're dividing by is. Okay? So if it's negative 4, I'm going to put 4 in. Because think about what that does. If x minus 4 is a factor, then 4 ends up being a 0. Does that make sense? Okay? So we're basically, eventually, when we start dealing with using this stuff to provide us something about our graph, we'll be checking. The synthetic division is checking for a 0. Okay? So we take x minus 4 being the factor, because that's what, when we do division, guys, if I give you like 10 divided by 5, okay, you get 2, right? So 10 was the dividend, 5 was the divisor, 2 was the quotient. But isn't 2 also a factor of the original 10? And the divisor of 5 is also a factor of the original dividend of 10, right? Okay? So when we do this, and this is the divisor of this, okay, we're also saying that x minus 4 then is a factor of this, because I can multiply x minus 4 by something to get back to this product. Okay? So if you remember that, so that's got to be the opposite of that term. Now we're going to put a line right there. Okay? And what happens here is that it's an algorithm. Again, it's another set of steps that you just repeat over and over and over until you're done. Okay? And we'll talk about how we know when we're done. But the first step of the algorithm says bring down your original coefficient. Bring down that first 6. Okay? And that first 6 then is analogous to you sitting here and thinking, okay, what do I need to multiply x by to get this 6x squared? Well, bringing that down tells me exactly what I need to multiply by. Okay? Now, you're going to take this 4 times S6. Okay? 4 times S6, and it gives you 24, right? Okay, we write that 24 underneath our second term. And that is analogous to you taking that 6x that you came up with and multiplying it by x and gives you 6x squared. And then you take that 6x and you distribute to the negative 4, right? So when I do this multiplication of that 4 times that, it's actually giving me what I need to subtract away from that term there. Okay? But the way we do this, because normally when we're subtracting, but because I'm not using negative 4, I'm using positive 4, it allows us just to do straight addition here. Does that make sense? So you're going to take your 4 times your 6, get your 24, then you're going to add those two things straight down, and it gives you 2. All right? And we just repeat the process. Take 4 times that 2, gives you 8. I guess this was negative 2, right? So it gives you negative 8. And then I'm going to add those straight down, and I get 4. And because there's nothing else after that 12, I know I'm done now. Okay? Now, a lot of times they'll do this, okay? At least I know I'm going to do this every time. I put a little line right there between my last term and second to last term. Because that tells me my last term is my what? My remainder. Okay? So my remainder, so that's R of x. Okay? This is my quotient, Q of x. Dividend, P of x. Divisor, D of x. Okay, now think about this. If my dividend was 6x squared, so I'm just going to look at the x squared term, and I divided it by my d of x, was x to the first, right? What's x squared divided by x? X, right? X to the first. So you took something squared, and you divided it by something x to the first. And that will then produce a line that starts with x to the first. That kind of make sense? Okay? So, what I end up here with is the exact same results. I get 6x minus 2 as my quotient. My divisor was x minus 4, and my remainder now is 4. And that is my dividend. If I multiply that out and add my 4, that is my dividend that I started with. Okay? But that process is a little bit easier, isn't it? A little bit quicker. Okay? And we're going to find out as well that there's some things that we can do with that process that allows us to kind of evaluate functions using pretty small numbers in comparison to the other techniques that we know about in regards to evaluating functions. Okay? So let's do this one. Okay, this one is one of those special cases that I said that we got to pay attention to. Okay, so if I look at that, is that polynomial in descending order? Yes. Okay. But what's the problem with it? What are we missing there? X to the first power, right? When you do synthetic division, okay, part of the algorithm says your polynomial needs to be in descending order. Okay, and we've got that. So make sure that on a test that you rearrange things. You follow that. Okay, don't just say that they're going to be real nice and convenient for me and they're just going to provide it the way I need to do the work. Does that make sense? You might have to do a little legwork first to get it in the right format so that you can do the synthetic division. Okay? What we need to do is write down our coefficients of 2, -7. But now because of that 0 term missing, we need to put that in there. Okay? This is really 2x cubed minus 7x squared plus 0x plus 5, right? And I need every single coefficient to show up, and 0 is a coefficient. All right? A lot of times in courses, in an Algebra 2 course, they might say, we need that placeholder. Okay? I don't know that's really a placeholder. It is a legitimate coefficient. All right? And we need it there so that when we go through our algorithm, things align the way they should. Okay? And we'll talk about that as we go through it, and we'll see where you would make a mistake if you didn't put that 0 in. Okay? So what goes in that box? What am I going to do synthetic division with? Yeah, I'm going to put It's always the opposite of that number right there. So I'm going to put 3 over here. Okay. First step is to bring your 2 down. Now multiply 3 and 2 gives you 6. Add those straight down gives you -1. Now 3 times -1 gives you -3. Multiply those, or sorry, add those gives me -3. And now multiply 3 and -3 gives you -9. And that should give you -4 back, right? Okay. My hope is that if you recognize that if you would have left that 0 out, you would have been basically taking that 5 and adding a -3 to it. Adding a -3 to it. And then you'd be done. Okay, and you would have had some problems. I don't know why that did that. There we go. Does that make sense, everybody? So if I would have eventually left that 5 there, so the 0 and the 5 kind of trade spots, and then I wipe away the 0, I'd be taking 5 plus a -3 gives me -2, and then I don't have anything over here, and I'd be done. So I'd have 2 minus 1 minus 2, and basically my quotient is of, or it's missing some terms, and it's also got some wrong coefficients. Okay, so now we got to pay attention to putting that placeholder of 0 in there. All right, so think about what happened here. This was x cubed, right? Okay, this was x minus 3, right? Okay, so when you take x cubed and divide it by x, what does that get you? X squared. So this line here is x squared, and then everything is in descending order. You will never skip over a term. Okay, so it's x squared and then minus 1x, and then minus 3x to the 0, which is just -3, right? Okay, so we're going to rewrite this as 2x squared minus x minus 3. That's your quotient. Multiply that by your divisor. Your divisor was x minus 3. And then add on to that your remainder of -4. Or you can subtract 4, however you want to write that. And that then is your polynomial, x cubed minus 7x squared plus 5. All right? It's just that this eventually becomes a more convenient way of looking at the polynomial than that way. Okay? And we'll talk about in the next couple slides situations where that convenience shows up. Does some of you guys remember doing some of this?
Yes.
All right. Let's go to, so PowerPoint, a lot of PowerPoint just walks you through those procedures with those examples in case you need to go back and look at how to do that again. Let's get down here to these called the remainder and factor theorem. These are two pretty simple theorems in regards to how they're written, but they become very useful to us in what we do. First one we'll talk about is the remainder theorem. And what the remainder theorem says, if the polynomial p of x is divided by x minus c. So what that means, we're dividing by a linear factor. We're dividing by like x minus 3 or x minus 4 or x plus 5 or x plus 12 or something like that. Okay? You're not dividing by x squared or x cubed or x to the fourth. Does that make sense? It's always x to the first power. So the polynomial p of x divided by x minus c, then the remainder that you end up with is exactly the same thing as p of c. Well, p of c is how we would evaluate the function, isn't it? Think about this. Think about one of the examples that we've done. Okay, I'll go back to the last one, which was was it 2x cubed? Anybody have that one there? Pick 2x cubed
Minus 7x squared plus 5.
plus 5. Okay, so that was p of x, right? We went through all of that and we found our remainder to be -4, correct? Or was it -4?
Yeah.
Okay, so the remainder became -4. So what we're saying here is because I divided p, what do we divide p of x by? X minus 3? Okay, so if I take, we had 2x cubed minus 7x squared plus 5 divided by x minus 3, right? Okay. When I find the remainder of that function, I found the remainder to be -4. That -4 is exactly the same thing as if you would take P and evaluate it at C, but evaluating it at C is that, right? Does that make sense, everybody? Okay. So if I evaluate this function at 3, I should get -4. Okay? Think about this. What's 3? 3 cubed is 27. 2 times 27 is 54, right? Minus then, 3 squared is 9. Times 7 would be, what, 63? So minus 63 plus 5. What's that give me? -4. Okay? Is that -4? That's P evaluated 3 is giving me -4. Is that the same thing as what my remainder was? Yeah, okay? But what is easier, when I did the synthetic division, when we did that right there, what's the biggest number you dealt with? -9, right? Okay. Up here, we had to evaluate things like 54 and 63. I'd use a lot bigger numbers, right? So the remainder theorem helps us maybe evaluate a function a little bit easier. Okay. Now, what's really nice is when that remainder becomes 0. Because when the remainder is 0, let's say for some fun, I don't know what the function is. Let's say we just have ax cubed plus bx squared plus c. Let's call it d. And we're going to divide by x minus c. If I evaluate p of c and I get 0 back, meaning that I do the synthetic division here and I get 0 back. Looking at it this way, p of c evaluated at 0, p of c is a y value, right? A y value is equal to 0 provides you a what? An x-intercept at that c term, right? Okay. So there's a lot of information kind of wrapped up in this theorem. Okay. We're interested in if the polynomial is divided by x minus c, then the remainder is the value of p of c. But it's even more useful, and we'll come back and do an example of that, but it's even more useful when we combine it, we'll get there, with this theorem here. And it says c is a 0 of p if and only if x minus c is a factor of p of x. Okay? C is a 0 of p if and only if x minus c is a factor of p of x. And the way we know that it's a factor of p of x is if our remainder becomes 0. Okay? And that then is allowed to be, it's an if and only if statement, so we're allowed to flip that and write it as if x minus c is a factor of p of x, then c is a 0 of p, right? Okay? So that's a two-way street there when you read that theorem. Factors provide you zeros, but zeros also provide you factors. Okay? So think about this. If I give you x minus 3 as a factor, you know 3 is a 0, right? But if I give you 3 as the 0, you should be able to work your way backwards and say, well, x minus 3 has to be the factor. Is that right, everybody? All right. And that is something you've been doing since Algebra 1, but now we're doing it with maybe some thought behind it and why we're doing it and what it means to us. So let's go back and do an additional example here. It says, let p of x equal 3x to the 5th plus 5x to the 4th minus 4x cubed plus 7x plus 3. And it says, find the quotient and remainder when p of x is divided by x plus 2. But then use the remainder theorem to see what p of negative 2 is. Okay? Well, I'm just going to jump straight down to the synthetic division here. Okay? So if it's x plus 2, then in my box is negative 2, right? And ultimately what we're doing here is we're evaluating the polynomial at negative 2. So that negative 2 right there. So I'm going to put my coefficients 3, 5, negative 4, 0, 7, and 3, right? Think about what we would be doing if all I asked you to find, and this goes back to what we did in the last chapter, if I say find p of negative 2, you would come up here and you'd say, okay, negative 2 to the 5th power is 32. Multiply by 3, get 96, right? And you write 96 down. Then you're going to take, well, negative 2 to the 4th power is 16. 5 times 16 is 80, you write 80 down. And then you go negative 2 to the 3rd power is negative 8. Negative 8 times negative 4 is 32. You write 32 down. And then you go negative 2 times 7 is negative 14. Write that down, and then add 3 to it, right? And then you sum all those numbers up, correct? Okay, just to find out what this thing evaluates at. Well, if I do synthetic division, think about the numbers that we're using here to do synthetic division. I'm going to bring down my 3. Multiply by negative 2 gives me negative 6. Add those together, I get negative 1. Multiply by my negative 2, and I put 2 there. Add those together, gives me negative 2. Take negative 2 times negative 2, and it gives me 4. Add those together, and get 4. Negative 2 times 4 gives me negative 8. Okay, add those together, I get negative 1. Multiply those two things together, negative 2 times negative 1 gives me 2. Add those together, and it gets 5, right? 5 is the remainder, right? So the remainder theorem that we just talked about said the remainder that you get is what P evaluated at negative 2 is equal to. So if I would have done that 96 plus 80 plus 32 minus 14 plus 3, I should still have gotten 5. But it's a lot easier because in that situation, the largest number I dealt with, negative 8, right? Okay? Nothing else up there. Or really the algebra up there, the mental math up there was very simple. Okay? And it's a lot more of an efficient process. Now obviously, we have calculators and technology that will allow me to evaluate that even faster, right? Okay? But this is a useful tool for some of the things that we do. The hope is eventually that we start to see that thing being a 0. Okay? That P of negative 2 gives me a remainder of 0. And this is why we'll do an example here, and then we'll elaborate on this a lot more tomorrow. Let's take this polynomial, okay? And let's divide, I think I'm going to divide it by, I'll find P of 1, okay? Well, the question says, let P of x be that polynomial, and then evaluate, or I guess prove, that P of 1 is equal to 0. Prove or show algebraically that P of 1 is 0. So, we're evaluating at 1, okay? So, let's think about what this means. This means that 1 is going to go in the box. I put my coefficients down of 1, 0, negative 7, and 6. Alright, now I'm going to bring my 1 down. Start going through this algorithm. 1 times 1. Put it there. Add straight down, gives me 1. 1 times 1 gives me 1. Add straight down, gives me negative 6. 1 times negative 6 gives me negative 6. Add straight down, what do you get? 0. And that's my remainder, right? Okay? So, think about what that means to us. If that's my remainder, then we know through the division algorithms that if this was x cubed and this was x, this would have been x minus 1, right? Okay? Then this becomes x squared, x, and minus 6, correct? So, my P of x, which is equal to x cubed minus 7x plus 6, is actually equal to my quotient, of x squared plus x minus 6 times the divisor of x minus 1. Does that make sense, everybody? Have we just factored x cubed minus 7x plus 6 a little bit? Let's go a little bit further. Because you know how to factor, once you get down this quadratic, do you know how to factor that quadratic even further? What's this thing going to factor to? X plus 3, x minus 2, and then you've got this x minus 1 here, right? So we know that x cubed minus 7x plus 6 just factored to x plus 3, x minus 2, x minus 1. And that is something that maybe you didn't know how to do initially, right? Okay, at the onset, we struggle with factoring x cubed, okay? Especially when there's not 4 terms, okay? But now using synthetic division, the factor theorem, and the remainder theorem, we're able to come up with x plus 3, x minus 2, x minus 1. Now, the reason that's useful to us, what's that tell you happens at -3 for my polynomial? X-intercept, right? What happens at positive 2? X-intercept. What happens at positive 1? X-intercept, okay? These are factors, okay? And it says if x minus c is a factor, then c is a 0, right? Okay, so we find those x-intercepts with those zeros. What is also kind of neat about this stuff is that once I get these, this c would have been -3, this one would have been 2, this one would have been 1. That also tells me that when I took x cubed minus 7x plus 6 and we divided that by x minus 1, I could have also divided by x plus 3, x minus 2, and x minus 1 and gotten down to another quadratic. So if I would have said, 1, -7, 0, 6, and instead of in this box putting 1, let's put 2 and see what happens. If I put 2, I go 1, 2, -5, -10, -10, what happened? Something wrong. 1, -7.
It's 0 before the -7.
Oh, I flip-flop? Yeah. Stupid. 0, -7. So bring my 1 down, 2, 2. Now I get 4, -3. 2 times -3 is -6. Gives me 0, right? So this would have also factored to x minus 2, x squared plus 2x minus 3. And again, you can factor that thing to -1 plus 3. Okay? We'll finish talking about this stuff tomorrow. Yeah, there is.